All right, so we're going to do lesson 61. It's still about vectors, of course. And this time, I think it's a word problem. I don't have my book in front of me. Do you see, like, I don't think it was a practice problem, but it was just from the lesson. There was like a ship and a boy on a ship or something. I don't know. I don't know if they drew any pictures or not. I'm just going by my notes. So, is it like a word problem, or do they kind of describe it out? Okay, so let's do that one. All right. So it says, we'll just do this. I'll just basically write down just a little bit of a sketch to what they want you to do. It says the ship is going northeast at 12 miles per hour, right? Do you see that in there? It's not a practice problem. It's like from the actual lesson that he taught. It should be probably pretty close to the beginning of 61. So look at where 61 starts teaching, and then it should be right at the beginning somewhere. And then the boy is going north. Do you see that anywhere?
North at 5 miles per hour.
Yeah, that's it. Show Emily where it is. She's still looking.
That one. Right at the beginning.
Yeah, it's right at the beginning. All right, so the ship is going northeast, and the boy's going north, and that's how fast they're going. I think, is the boy on the ship? He might be on the ship and walking. Yeah, that kind of thing. All right, so this is what we would do to figure out his the resultant velocity. Now, because the boy's on a ship, watch this. I don't know if I can do this on here or not, but we're here. We're starting here, and the ship is going like this, right? And the boy is walking north, but as the ship is moving, he's moving as well. Okay, so he's actually doing what? He's actually kind of going in this direction right here, wouldn't he be? Because he's going forward, the ship is going this way. So, of course, the ship is not just one little skinny line. Okay, it's got some width to it. All right, so the boy is kind of walking like this. Does that make sense? So his actual path, like if you were to look from the sky and have like an X and Y axis, and you were just to look at his path and kind of have like an invisible boat, right? Pretend your boat was invisible, and you see the boy, and where would he actually wouldn't be walking in that direction. What would he be doing? He'd be kind of walking in this direction, wouldn't he? All right, do you see that? Can you imagine that? It's hard to show on this screen right here, but that's what's going on. All right, so what do? What do we add the vectors together? So if you want to find the resultant vector, and I think that's what they basically are asking for, or telling you to find, like the resultant vector. What's the resultant vector of the combination of these two right here? So let's do a couple different colors here. Make them stand out a little bit. Northeast. Okay, well, this is north, right? And this is east. So northeast would be going right between the two of them. So how many degrees would that be? 45 degrees. So if it just says northeast, that would be going 45 degrees. All right, so this is the direction the ship is going, and the length of the vector is 12, okay, because that's the velocity, that's the speed, 12 miles per hour, and this is 45 degrees, okay? So the ship is going in that direction. Now remember, the kid's on the ship, right? The boy. And what's he doing? He's walking north, right? The boat's going northeast, but he's walking north. So watch this. It's like this. Well, he's going like this. The boat's going. So he's sitting on the boat, right? So he's like right here on the boat. The boat's going like this, and he's walking. And see what's going on? See, he's going north, but the boat's pushing him that way. So he's kind of going like that. Can't see that on the computer screen, but hopefully that makes a little sense. All right, so what do? We put the vector right here. We start right here, and he's only going 5 miles per hour. He's not going, as fast as the ship is going, so we don't make the line as long. All right, so we kind of make that little line a little thicker just so we can see it a little better. There we go. Okay, and so he's going north, which is 90 degrees, and he's going 5. So what we want to do is we're going to add those vectors together. That's what we're going to do. All right. There's several different ways you can add the vectors together, but the way that he's showing you in the book is breaking both of them down into its components, right? Taking the components, adding them together, add the x's together and the y's together, then taking that component vector, changing it back into magnitude and direction, okay, with a length and an angle, right? So I think we've talked, I don't know if we've done all that together, but we've done them separately. We've taken a vector, changed it into its components, haven't we? And we've taken a component vector and changed it into a, I don't know what they call it, but just a regular vector with a magnitude and direction, all right? And that's what we're doing right here. So let's take, let's do this in red since we're in colors here. Let's take the boy right here, and let's figure out how we're going to do this. I'll just do like a little mini. Actually, let's do this in whites. Then we'll do the vector in red. All right, so what's it doing? It's going 5, right, like this. Now, if we break it down into its components, we don't go left or right at all, do we? So what is the component vector? How far did we go left and right in order to get to there? We went 0. How far up did you go? We went 5, right, because the length of that is 5. All right, so the component vector of the boy was easy, wasn't it? So if you're just going north or west or south or east, it's really simple. It's going to have a 0 in there. All right, so it's just 0, 5. So my component vector, sometimes we'll do this. Remember the I and J thing? It seems like he does that a lot, and you will see that quite a bit. So we'll write 0i plus 5j. Is that okay? Yep. All right, let's do the ship. And we'll do this right here. Kind of slide it in here. So let's do the ship. Let's put our little x and y axis right here. Let's get rid of this little red thing. All right. And what is it doing? It's going like this, isn't it? Now, how in the world, well, we know the length of it. It's 12, right? How do we find the component vector? Do you remember how to do that? So if it's going here at 45 degrees, remember we take this down to the x-axis? Remember we always make a right triangle out of it? So we take it down to the x-axis, and then we have to find what the x is and then what the y is. The last time we did this in class, we kind of, you could look at it and say, okay, this is x and this is y, this is adjacent, this is hypotenuse, so it's cosine. But you get so used to it and you get so consistent with this, there comes a point where you don't even have to think about, oh, is that the sine, that's the cosine. There comes a point, and we did this, if you watched the video from last time, we said that the x is always going to be the hypotenuse times the cosine of the angle. Do you remember talking about that? Right? It works out that way, right? You could have gone the cosine of 45 equals adjacent over hypotenuse, x over 12, and then you can multiply both sides by 12. So x is going to be 12 times the cosine of 45, right? And we can put that into a calculator, and that comes approximately 8.5. Right? We'll just use decimals with this. And this one's going to be the same exact thing. Let me give myself, oops, a little bit extra room. This one's going to be the same thing, except it's not going to be cosine. What's it going to be? Sine, because this is opposite over hypotenuse. So this is going to be the hypotenuse times the sine of the angle. Okay? Now, the sine of 45 and the cosine of 45 are exactly the same thing. So that would also be 8.5. You can put it in your calculator, figure it out. But when you have a 45 degree, because look, think about it. You went over just as far as you went up, didn't you? So the x and the y must be the same length if it's 45 degrees. You with me on that? I take that silence as a yes. Okay. So let's write this as an I and a j. So I've got 8.5i plus 8.5j. So we broke it down into components. Now, what do we do now that we have it into its components? We want to find the resultant vector. So what do? We add them up. Okay? So I'm going to take this one, and I'm going to add it to this one right here. Now, how do we add component forms of a vector? Well, it's actually pretty easy. Add the x's together, add the y's together. Okay? Or in this case, the i's and the j's. So 0 plus 8.5, 8.5. And then 5 and 8.5, what's that, 13.5? Okay, and that's j. And there you go. But that doesn't give us the magnitude and the direction, does it? That's the component form of it, but guess what we're going to have to do now? We're going to have to take this component form and change it into a magnitude and a direction. So we're going to have to plot this again on our x and y axis. Aren't you glad in Algebra 1 you learned how to do the plotting of these things? All right, so let's do this. We start here. It's positive 8.5, so we're going to go to the right, approximately 8.5, whatever that is, and then we're going to go up 13.5. So the up's got to be a little bit longer, doesn't it? All right, you with me? So this is the x part of the component, and that's the y part of the component, and we just make a right triangle out of it. Let's do that in that pretty color. All right, so this, what's that look like, pink or purple? It's hard to tell. It's kind of light in here. Pink, we'll call it pink. Okay, so the pink one right here is the resultant vector. This is what we're trying to find. Okay, this is what we're looking for right here. I'll call it, they call it S plus B, ship plus the boy. I'll call it R for resultant vector. Is that okay? Because that's a lot of times we call the answer to a vector problem a resultant. So I'll just call it R. All right, so now what do? Should be kind of easy now. We know the length of this bottom one. What was the length of that bottom one? 8.5. What was the length of the y? 13.5. So what are we going to do to solve for r? Pythagorean Theorem. Very good. So you go r squared equals 8.5 squared plus 13.5 squared. And I'll save you all the work. I wrote it down somewhere. Where did I put it? It's around 16. Okay, so it's around 16. It's approximately. I don't think it's exactly, but it's pretty close. All right, so that's our magnitude, right? Because they ask for magnitude and direction. So now, where's the direction? The direction is this angle right here. So we have to find that angle. Well, how do we find that angle? I've got this and this. This is opposite. This is what? Adjacent. So what am I going to use? I've got a right triangle. So what am I going to use if I have opposite and adjacent? Tangent. Good. Okay, so I've got the tangent of theta is equal to the opposite over the adjacent. All right, put that in your calculator. Take the inverse tangent to get theta by itself, and you get about 57.8 degrees. Oops, not squared. What am I doing? Degrees. You could write it several different ways. This is how I would write it. I would say the resultant vector is 16. This is miles per hour, right? Because that's how fast they're walking. At 57.8 degrees. You might write it a little bit different, but it's basically that, okay? Doesn't have to be exactly the way I wrote it, but that's kind of how I like to do it. So the resultant vector is 16 miles per hour at 57.8 degrees. So again, remember somebody's on a helicopter looking straight down at the invisible ship, right? And they're looking at the buoy. And what is the buoy doing? It looks like he's going in this direction. Do you see that? From the airplane or from the helicopter, he's looking down. It looks like the buoy is going in this direction at 16 miles per hour, right? That's what it looks like he's doing. Because you added his velocity plus the velocity of the ship, right? You didn't just add them 5 plus 12, though, and get 17, did you? You had to add them vectorially, right? Which means you got to take and consider the direction that it's going. So you add those together, you get 16, and you also found your angle. It was like 57, right? 0.8 degrees. And so that angle that he's going is greater than 45, so that's the direction that the buoy looks like he's going, right? You make everything else invisible, and you put a little clock on him, right? Like a stop. What do you call those things in baseball? The gun, the pitch gun. What do you call it? You watch baseball, don't you? The speed gun. Yeah, that's what you call it. You ever see that where the guys hold it up and they figure out how fast the pitches are going? So he's got one of those, and I'm like, okay, he's going 16 miles per hour, and he's going at 57.8 degrees. All right? Okay, enough of that. I explained that a little too much. I think the other ones can go a little bit quicker since I gave a basic explanation of it. All right? So let's do another one. That was like miles per hour is velocity. Well, you can do that with force as well. It's the same thing. They're all vectors, so it doesn't matter if it's force, doesn't matter if it's velocity. It's still adding vectors the same exact way. So here's the situation. I think it might be the next one on there. Do you see it? It's like, is it 2 billiard balls or something like that hitting another one? Is that the deal? Again, I just took sketchy notes on this, so I don't know exactly what it's. I just have a. So you have a ball right here, right? And then you got a force coming from here, pushing the ball, and it's going like 30 degrees. About like that. You see that on there? I think they have it drawn on there somewhere. Okay. And this is 30 degrees. And it says it's a force of 90 newtons. Newtons is a unit of force. I'll just put a 90 right there, okay? So it's a force of 90, so that's the length of that line, and it's going 30 degrees in that direction. So it's kind of like your force is coming, like the ball is coming from this direction, it hits, and it goes like that, right? And then there's another force acting on the same ball, because there's like 2 balls hitting it at the same time, right? One's hitting like this, and it comes up at like 40 degrees. And this is a larger force, so the force is bigger. Either the ball was going faster, or the ball might have weighed more, or something like that. So this force was 150 newtons. And this time, oops, not 45, it's going at 40 degrees. Okay? So that's the situation. Does that make any sense so far? You got this ball, you got one ball coming from this direction, hitting it at a 90 Newton force. You got another ball hitting it at the same exact time, right? Hitting it at the same exact time, and that force is going that direction. So, which direction will the ball actually go? You understand? You got a ball just sitting here, right? One ball's coming here, one ball's coming here. They hit them, boom, at the same time, and then that ball that's right here, it goes off. It can't go off twice. It's not like it's split in half and one ball goes one way, or half of it goes one way, half of it goes the other. Okay, where do you think that ball's going to go?
Slightly towards 150.
Yeah, that's good. I like that. It's slightly towards 150. So it's probably around here somewhere, wouldn't you think? Okay, that's what my guess would be. Somewhere probably about like that. So that's where the ball is going to actually end up, right? And you add the 2 forces together, so this will be a greater force, right? Because 2 different forces were added together to hit it. But it's not 150 plus 90, so it's not going to be a 240 Newton force, because not all the force was acting in the same direction. That's more physics stuff, okay? This is definitely a physics topic. If you ever take a physics class, you'll be ready for it, because you'll say, oh yeah, we did that in pre-calc, okay? So no big deal. All right, so that's basically what it's going to look like. So what we're going to do here is we're going to add those 2 forces together, all right? Tell you what, just to make this look a little prettier. Let's make this a different color. There we go. Oops. Anyway, who cares? So what we're going to do is we're going to break them both down into its components. So let's make a little x and y axis. You could do it right up there in that picture, but then it gets a little messy because you got all these triangles, you know, in the picture. Sometimes you don't have to do it like this, but sometimes it's nicer just to, oops, what did I just do? Something. Wow, that was weird. Sorry, a little slow here. Okay, let's get back to the blue. All right, so what's going on? This is going 40 degrees at 150. All right. Ever heard a bell go off? Or,
Every hour.
does it? Do you guys usually hear it when we're in here? I've never heard it in here. Wow.
They've had it off for a while.
Oh, is that what it is? Okay.
It normally goes off every hour.
Okay. Guessing.
It's been off for a couple minutes. It's been working.
Oh, maybe that's why. All right, so that's at 40 degrees, and it's 150. So we're going to break that down into its components. Let's draw them both out, and then we'll break them down as components kind of at the same time, okay? So let's do the yellow one next. Okay. And that goes 30 degrees. It's a little shorter. Doesn't have to be exactly to scale. It's not that big of a deal. and that's 90 newtons, and that angle is 30 degrees. Okay, now we're ready to break them down into its components. All right, so what are we going to do? Well, we're going to drop this straight down, aren't we? Make a right triangle out of it, and we want to find the x and the y. Now, remember what we did? This saves you a lot of time if you can remember this. What's the x component going to be?
12 cosine.
Well,
150 cosine.
You got it, good. You see that? All right, so you could say, okay, the cosine of 40 is x over 150, then do your math and solve for x. But instead of doing that every single time, you recognize it's going to work out this way every single time. It's the hypotenuse times the cosine of the angle. And then this y value is the hypotenuse times the sine of the angle. And that's kind of nice. So the cosine, I'll save you the work if I can find it right here. What is it? 150 times the cosine of 40. That's 114.9. You can put that in your calculator yourself. And then the other one was 96.4. Okay? And then we can write it out as a component. 114.9, put an I right there, plus 96.4, and put a J right there. Now, they're both going positive too, aren't they? The x is going to the right, and then the y is going up, so they're both positive. Now, you're going to have to take that in consideration with this next one right here. All right, so make sure that you see that. So what are we going to do with this? We're going to drop this one up to the x-axis. And now here is our x, so what's our x going to be? It's going to be 90 times the cosine of 30. See how easy it is without, going through the whole cosine and sine thing? And this is going to be 90 times the sine of 30 degrees. Okay? And I'll just tell you what those are. The cosine is 77.9, and the sine is just 45. Because the sine of 30 is a half. Half of 90 is 45. So it's 77.9 I. Now that's positive, isn't it? But what about the 45? This is going down. So what sign are we going to put here? We got to put negative. All right, that's very important. Sometimes that's very easy to forget about. But you got to take in consideration the direction that these things are going. Okay, so this y direction was going down, so you got to put a negative. See that? It's positive 77.9, negative 45. Now we're going to add these together. Okay, so you add them together, and I'll add them for you. The 114.9 and the 77.9 is 192.8. That's in the I direction. And then you add the j's together, 96.4 minus 45. And that's a positive 51.4, and that's a J. But we're not done, because they want a magnitude and they want a direction, don't they? After a while, you may not have to draw this x and y axis, but I like to do it at first because it just kind of makes things where you could see it, and you know exactly why you're doing what you're doing. So it goes over 198, so it goes over quite a bit, doesn't it? And then it goes up just a little bit, 51.4. And remember what we said? You said it goes just a little bit higher than that x-axis. Remember this one right here? We said it just goes a little bit higher. And look at that. It's exactly what it does. See that? So that is the direction that we thought that vector was going to go, didn't we? All right, so that's our resultant vector. Okay, this is our x, and that's our y. Actually, we can put the numbers in here. Let's put the numbers in here instead of putting x and y. So this is 192.8, and this is 51.4, and this is theta. You got to find that angle. So it's just Pythagorean Theorem. So do Pythagorean Theorem. I'll just set it up for you, then I'll show you what the answer is. You should put a square here. Plus 51.4, and that's squared. Then you solve for r, and you do all that. It's 199.5. And that's newtons. That's a unit of force, okay? Again, if you take a physics class, you'll learn about what newtons are. And then you got to find the angle. You find the angle by taking the tangent, and so that's opposite over adjacent. Then you take the inverse tangent, so theta is equal to about 14.9 degrees. Remember you said it was just a little bit higher than the x-axis, wasn't it? And 14.9 is just a little bit higher. So if I want to write this out real nice, the resultant vector is 199.5 newtons at 14.9 degrees. I think he just answers them separately. I think he like circles this one and he circles this one. But I kind of like this. This kind of puts it all together in one nice little package. I think that's kind of nice. All right, you getting the idea with that? All right. I think we've done enough of that adding vectors. In a couple of practice problems, they had some adding vector stuff. Trying to find one. Let's do another vector one before we. That one, the dot product. That's right. I didn't staple this in very good order. I thought I did. Trying to think of a good one. Yeah, let's do this. There are times. I don't think they give you a real. I don't think they give you an example of how this can be used in real life. They're just kind of introducing it to you. So if you see it later, you're like, oh, okay, I've seen that before. I kind of recognize it. We've learned how to add the vectors together. Let's see how we multiply vectors together. All right, so I'm going to take a vector v and a vector u, and I'm going to multiply them together. Now remember, this is a vector, so it has an x component and it's got a y component. Okay, does that make sense? Because look, if you have a vector like this, right, it's got an x component and it has a y component. Would you agree? So if I call this v, vector v, I'm going to call this, watch what I'm going to do this. I'm going to call this v sub x, or just vx. That means it's the v vector, but it's the x component, right? It's the x part of the v vector. Does that make sense? And this would be what? What do you think this would be? V what? Vy. Good. All right, so what we're going to do is this vector has two components. It's got vx and it's got vy. Well, if you had a u vector, it'd be the same thing. You'd have what? U x and uy. Good. Okay? Does that make sense? So this is how we multiply them together, because we got two things that we have, right? This v vector is vx comma vy. Do you agree? And if you had a u vector, it would be ux and uy. How do I multiply those together? Do I just multiply these together and these together? I wish it would be that easy, but it's not. It's not much more difficult, but it's not quite as easy as doing that. All right? It's a little bit different. Let me just show you what it is. It's vx times ux. All right? So you are multiplying these two together, and then you are multiplying the v and the u's together. Watch this. Vy and uy. But here's something you might have not thought about. You actually add the two products together. All right? So you're multiplying these two together, and you're multiplying these two together, but you don't multiply all that together. You add those two products together. All right? So you multiply the x's together, you multiply the y's together, and then you take those two numbers and you add them up, and then that's your finished product. Okay? So this is multiplying vectors. They call it the dot product. All right? The dot because of that thing right there, because you're multiplying. They call it the dot product rule or something. And this is when you multiply vectors together. All right? All right, let's just do a quick example with this. I don't think they give you any like real life examples with this. They just say, here's two vectors, multiply them together. All right? And to tell you the truth, I can't think of a great example where you would use this, but I know I've used it before. I remember taking physics classes and stuff, and we had to do dot product. So it's definitely something that you use. But they're just trying to introduce it to you right now. It's negative 2, 4. Okay? All right, so here's our two vectors, and I want to multiply them together. I want to find this. I want to find vector v dot, or times, vector u. So how do I multiply them together? Well, I just multiply the x's together. So that'd be 5 times negative 2. Then I multiply the y's together. That'd be 7 times 4. Then what do I do to those? I don't multiply all that together at once. What do I do to those two things? What did my dot product say? Add them, right? So you add them together. That's all there is to it. Okay, so that's negative 10, that's 28, and that's 18. So if I multiplied these two together, if I asked you to multiply those two vectors together, you would just get 18. Okay? And it's actually, it doesn't even come out to a vector. It's kind of crazy. It's when you multiply two vectors together, you just get just a regular whole number. Okay? Or it's not necessarily a whole number, but you get a number. This is called a scalar. When it's just a regular old number, there's no direction associated with it, we call that a scalar. When there's a magnitude and a direction, we call that a vector. Right? So that's pretty important right there. All right? There's a few other things in that lesson. I mean, he taught it, and there, you know, and he goes over the problems and stuff. But I just wanted to make sure that I hit some stuff so you could kind of hear my explanation of it as well. I don't know if it made it better or worse for you, but that was it. Let me see. Yeah. Yeah, I guess that's good enough. All right, let's take a look at 62. Let's change colors. I'm tired of that green. Let's get yellow. This parametric equation stuff. This is another physics-related thing. Here's the situation. I think the first one is like, I don't know, somebody kicked a ball or hit a golf ball or something like that, right? So here's the ground, all right? And what you have is you have like a ball right here. We'll say it's a golf ball. And he hits the golf ball at a certain speed, and he hits it at a certain angle. And we can actually find, just by knowing that, just by knowing the speed at which he hits the ball and knowing the angle that the ball goes off, we can actually find a lot of things. We can actually find like how far the ball travels. We can find out how far. We can find out how long it takes. All kinds of stuff. Isn't that amazing? Just from knowing that little vector. So I'm going to draw this vector as a straight line first. And what do they say? 30 degrees. So we'll make it kind of skinny. So it's initially hit at 30 degrees, and with not a force, but it goes with a speed of 150, and this is feet per second. All right? What they want you to do first, before they do anything, what they want you to, the most important thing here is to break it down into its components, okay? Just like we did before. So this is kind of like an offshoot of lesson 61. So what I'm going to do is I'm going to make a x and y axis, and we're going to break it down into its components. Now, the more and more you do this, the less and less you're going to have to rely on this new x and y axis. You might just be able to figure it out on your own, to tell you the truth. But I don't want to assume that, so I'll just make this a little bit larger so we get a little room to work with. All right, so there's our vector. The magnitude is 150 and the angle is 30. What I want to do is break it down into its components. So you should be able to do that pretty easy now. Would you agree? So what's the x component going to be? It's going to be 150 cosine of 30, right? And what's the y component going to be? 150 times the sine of 30, all right? That's pretty easy. So the x comes out to around 130 feet per second. Feet per second. And this will come out 75 because the sine of 30 is a half, isn't it? Remember that? So that would be half of 50, or 150, which is 75, and that would be feet per second. So this golf ball travels, basically it travels in two directions. It travels in an x direction at 130 feet per second, and it travels in the y direction at 75 feet per second. But there's an issue, all right? Talking about the y direction, like if I drop something or if I threw something up in the air. If I threw something up in the air at a certain speed, is it going to continue with that speed forever and ever? No. Something's pushing down on it. What's pushing down on it? Gravity's pushing down on it, okay? So we have to consider that as well. So what we're going to do is this. So we know v for velocity, okay? We know the x direction of our velocity is 130. And we know the y direction of the velocity is 75, right? Now, we have a little formula in physics, and you probably learned this before. Do you ever remember this? That the distance is equal to the velocity times time. Distance equals rate times time. You ever hear that one? The rate in this case is velocity, so we're going to put a v in for this. So this is something that we have known for a little while, probably. And so what I'm going to do is this. I'm going to use the letter x to represent the distance that the ball travels in the x direction, okay? So x is going to be the distance. I could put dx if I wanted to, but we're just going to write x. So what are we going to do? X equals the velocity times the time. Well, what velocity? It's the vx, because it's the velocity in the x direction, right? And then I multiply it by the time. So I can write a little formula here. I can write x equals 130t, because remember vx was 130? I know this might sound like a little mumbo jumbo right now, but you know, the more you do it, the more it makes sense. Now, that was the easy part, okay? Because the x direction, gravity's not acting on it in the x direction, does it? It just acts on it up and down in the y direction. So we have to know a little bit about this. Let's say we did not consider gravity whatsoever. How would I write this? I'd say, well, the y direction is what? See, this is, or the y distance equals the y velocity, so vy times the time. But the problem is that's assuming that there's no gravity, right? We have to take in consideration the gravity. Let's do this. Y equals, and then vy was what? 75t. We have to take in consideration the gravity, and so we say that gravity acts at negative 16 times t squared. You're like, where'd that come from? It's just something that people know, all right? You don't have to worry about where it came from. This is what we know about gravity, all right? So it's actually acting in that direction. It's negative because which way is gravity acting? Down. So that's why the negative, and it's 16 t squared. It's talking about acceleration and all this stuff. That's physics, okay? We're just trying to deal with the math part of this. So what are we going to do here? We have to take this into consideration. So I have to add this to this thing right here. All right. So this is what I'm going to add to this. So y, this again, what does the y mean? It means the vertical distance. Okay, the distance that it's going in the y direction. And of course, watch, as the ball travels like this, that distance changes, doesn't it? Right? So it's always going to change. So depending on how many seconds, the distance changes, right? For every second that ticks by, the distance actually changes. And so that's what it's saying. So I've got 75t, and I'm going to add it to this negative 16, or just put minus. Actually, they put the squared thing first. Let's do that. So negative 16t squared plus 75t. Now again, where did this come from? It seemed like it came out of the blue. It's just something that people already knew. They've done experiments to figure out what the acceleration of gravity is, okay? And so you just add that to this, and that's the distance. So like after 1 second, you could actually figure out how far this thing has traveled after 1 second. How would you do that? Plug in a 1, right? You'd plug in a 1. How far did it travel vertically after 3 seconds? Plug in a 3 for the t, right? Work it all out, and you got how far it goes up and down in 3 seconds. Same thing with the horizontal direction. How far did it go after 1 second? Well, 130 times 1. So it went 130 feet. In 1 second, it went 130 feet. In 2 seconds, it went 130 times 2, which is 260 feet. Follow me on that? Okay, so that's what this stuff is telling you right here. And yeah, I wrote that down for 1 second, 2 seconds, but you could do that if you want to, right? At 1 second, so watch this. At 1 second, the x would be what? 130 times 1, which would be 130 feet. All right? The distance after 1 second on the y, let's do it right here. Y would be what? Negative 16 times 1 squared plus 75 times 1. And you put that in your calculator, and you get about 59. So it would go 59 feet high. After 1 second, it goes 130 feet horizontally, and it goes 59 feet high. If you put 2 seconds in here, watch. At 2 seconds, I won't write it all in here, but the x is 260 feet, like we said before, That makes sense, doesn't it? 130 times 2. And then the y, I stick a 2 in for the t, and I stick a 2 in for the t right there, and it comes out to 86 feet. You see that? Now look, it didn't completely double, did it? You'd think after 2 seconds it would go twice as high, but it doesn't go twice as high. What would twice as high be right here? It'd be like 118, wouldn't it? It only went up 86. Why didn't it go twice as high? The horizontal distance went twice. It went from 130 to 260. Why did the vertical distance not go twice as high? Because of the negative, right, and because of gravity, right, because gravity's pushing against it. It wants to go, right, as fast as it can, but gravity's pushing against it. So that's why it doesn't go up near as high. Does that make sense? Okay, so those numbers kind of work for us. Here's the big question they're going to ask, and we'll probably be done with this. But I think what we're doing right here, I think helps you a lot with this one particular lesson. They're going to ask you, how long did it take for the whole entire flight of the ball? All right? And you have to figure out what the time is. That's the key. All right? So that's a little crazy. Watch. The ball is hit like this, and it goes in a parabolic motion. You ever hear that word? Parabola. And I didn't make my I'll make my distance match up with the ball. It's not a bad parabola, is it? All right, so what do we have here? So it goes off at 150 at 30 degrees, and what was the time? Before he even hit it, what was the time? The time was 0, wasn't it? What was the time right here? We don't know, right? We don't know how long it took to go there. But we do know something else. We do know what was the y distance right when he hit it. What was the y, or right before he hit it? What was the y distance? How far did it travel in the y direction? 0, right? But then it went up, 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 up to here. This is the highest that it went. But then what's it start doing? It starts going down, 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 until right here when we're trying to figure out how long it took, what was our y distance here? It's 0, isn't it? Okay? So that's kind of important. Remember what our little formula was? Y equals negative 16t squared plus 75t. Remember that? Look at this. What is that y? That's the y distance. So I can actually find t if I put a 0 in for y, right? Because the y distance here is 0. If I put a 0 in for y and I do some math and I solve for t, which I can, right? I could put this, let's see. Yeah, I could factor this. I could factor out a t, right? You get negative 16t plus 75, right? Set that equal to 0, so you get t equals 0, and then you put that in there, just to save some time, you get about 4.7 seconds, right? You know it's not going to take 0 seconds to go all that direction, right? So you throw out the 0. What's the other number? 4.7. So how long did it take to get here? It took 4.7 seconds. Now, you could find out the horizontal distance that it actually traveled. Look at that. So we'll call that x. Remember what our formula was for that x? X was just 130 times t. Now, how long did it take to go that whole entire distance? 4.7 seconds. So I could go 130 times 4.7, chuck that in there, and I get 611 feet. So look at that. Just knowing the speed that the ball was going and the angle, I could figure out actually how far that thing actually traveled. And I could figure out how much time it took to travel that distance. I could also figure out something else. I could figure out how high it went. Let's do this in a different color. I've got too much yellow. Watch, I could figure out how high it actually traveled. What's the top height? It would be right there, wouldn't it? What do you think the time would be at this point right here? Where do you think that is in the whole scheme of this, the path of the ball? It took 4.7 seconds here. At the total height, it's half of it, exactly right. And that time would be about 2.3. So this time right here, about 2.35 seconds. Okay? And you can actually find now, watch, remember this formula? That's the height, isn't it? The y is the y height. So now I know what my time is, so how can I find my height right here? I could go negative 16 times t. What's my t? 2.35. square it, plus 75 times 2.35, almost done, I know you got to go. Y equals, and you put it in here, it's about 87.9 feet. Look at that. Isn't that amazing? Just from that little information, just knowing the speed and the angle that that ball went, look what we figured out. We figured out how long it took to make the whole entire trip, right? We figured out how long the whole entire trip was, right? The distance that it traveled. And we also figured out the vertical height, how high it was, okay, at its top of its flight. Isn't that pretty cool? And there you go. So that should help you out a little bit with 62. A lot of that stuff all boils down to what we just did right there. Okay? Hope that helps. And it's time to go.